Hello everyone, I'm Vivekanand Talgadi, your chemistry instructor. Today we will be taking a look into the polymers, right? So when we speak about the polymers, remember that this term as a polymer is taken from the Greek literature, which means poly. Okay, poly refers to many, while mers is nothing more than it is a unit. Okay, now when we take a look at a polymer, actually a polymer is a huge chain-like structure. Okay, now these huge chain-like structures are actually formed from a series of smaller units. Okay, these smaller units are actually connected to each other by the help of covalent bonds. So remember this, the bond which is present between the two smaller units is actually a covalent bond. Okay, so there is a covalent bond over here, here, like this. So when there is a huge number of covalent bond between these monomers, what is going to happen is whatever the substance, whatever this particular molecule that we are going to get, which is a polymer, it is going to have a huge molecular mass. And the molecular mass of these polymers is going to be in the range of 10 raised to 3 atomic mass unit to 10 raised to 7 atomic mass unit. This is how it all goes. Okay, now these smaller units which are there, which are connecting to one another in order to give rise to polymers, these smaller units we call them as monomers. Okay, now because of the huge molecular mass, our polymers are going to be called by the another name. They also have another name. The other name for polymers is macromers. Okay, so let's understand all of these points in detail one by one. So poly refers as many, mers refers to units. So here is a simple representation of a polymer. Now if you can see that there is a smaller section over here which is a repeating unit. Okay, so this repeating unit, because of this repeating unit, what is going to happen? One repeating unit is going to get connected to the another repeating unit by the help of a covalent bond. Okay, now these smaller repeating units, of course, we call them as monomers, and the bond between the two monomers is going to be as the covalent bond. Now, due to this, these are going to have a larger molecular mass, and that particular mass ranges from 10 raised to 3 to 10 raised to 7 U. While these are also called as a macromers because of their huge molecular mass. Okay. While the smaller repeating units, we call them as monomers, which we have already seen. Now, the process of connecting one monomeric unit to the another monomeric unit. Okay, this entire process, we call it as a polymerization, right? So this is about the slide one. Now, as we go for the next, here you are going to take a look into the example wherein a monomer unit, that is the ethene, is getting converted into a polyethene. This is an example for the process of polymerization. Now let's try to understand here. Now here, if you see this unit, this is a smaller unit, and this smaller unit is our ethene. It refers to the two carbon systems, while E and E refers that in this particular molecule, we have a double bond at this position, right? Now, what is going to happen is large number of ethene molecule polymerizes in order to form a chain-like structure. The chain-like structure looks something like this. This double bond gets converted into a single bond so that it gets connected to the next molecule, something like this. Okay, so this chain goes on continuing depending upon the number of ethene molecules that we have. Okay, so this was the molecule what you get. Over here we term it as poly. Poly means many. Many ethene molecules have combined. So we call it as a polyethene. Okay, now when we take a look into the next one, that is the formation of the second type of polymerized unit, and that particular molecule we call it as nylon 6,6. So in nylon 6,6 we use adipic acid and hexamethylene diamine. Okay, so here what is going to happen is that these in adipic acid, this section, that is the COOH, the OH section of the carboxylic unit is going to react with one hydrogen of the amine. Okay, that means these react. When these react, there is the formation of water molecule. Okay, so when there is a formation of water molecule, the water molecule is liberated out, and whatever the unit, the whatever polymer that you get over here, this polymer, we call it as the nylon 6,6. Now, why it is called as nylon 6,6? Observe here. This is a first carbon. Okay, now there are 4 carbons as a chain in between. So here you have a 4, right? So 1 plus 4, that is 5. 5 plus 1, that is 6. After 6 carbon, you have your nitrogen over here. Okay, and after that, another 6 carbon gap, and then you have another nitrogen. So therefore, the nitrogens have been placed exactly after 6 carbon. So hence, we call it as the nylon 6,6. Okay, so this is how it all goes. So let's observe the next. So here, we can also classify these polymers, whatever the polymer that we have, usually these polymers are classified into 3 classes. Okay, so our first class actually is from what source are we getting these polymers? Are we getting these polymers from the natural sources? If that is the case, we call them as the natural polymers. Okay, in case if we are getting the polymer right from the natural resources. While if we are going to take, or if we are getting the polymer from the labs, if we are synthesizing them in the industries, in such cases, we call them as synthetic polymers. Okay, while if the particular polymer is actually a derivative, it is a natural polymer, but we are going to make certain changes in these. These are going to be derivatives of natural polymers. We are taking those polymers from the natural sources, we are adding some chemicals to it, making it a little bit stiffer, making it some more better in its character. In such a case, these polymers, we call them as semi-synthetic polymers. Okay, so we are going to classify the polymers into 3 categories depending upon its sources. Okay, so this depends upon the source. So depending upon the sources, we have the 3 categories. Category number 1, natural polymer, 2, semi-synthetic polymer, 3, a synthetic polymer. If we take a look into the structure, that is the classification of polymers on the basis of structure. Okay, on the basis of structure, again, we can have the classification into 3 classes. 1, it is called as the linear polymers. Okay, second one we have is the branched polymers. And the third category is called as cross-linked polymers. Okay, so we actually have these three again. On the basis of mode of polymerization, okay, how are we creating this polymer? So on the basis of the mode of polymerization, again, we can classify these polymers into three categories. So our the third type of classification of these polymers, that is on the basis of mode of polymerization. Okay, so on the basis of mode of polymerization, we can have into two categories. The one is that we can have this mode of polymers is on the basis of whether we are forming these polymers by the addition polymerization. Remember this, whether we are getting those particular polymer by the help of the process addition polymerization, or whether the mode of polymerization is the condensation polymerization. Okay, so we will understand these when we are speaking in detail about this, which we shall do it in the future classes. Okay, so this was all about the classification. So first point, that what we had was on the basis of classification, the polymers are classified into several categories depending upon their source, structure, mode of polymerization, and yes, molecular forces which are involved in those particular polymers. So, on the basis of sources which we have already discussed, that is, on the basis of polymer sources, these are categorized into the natural polymers. That is, these are the polymers which are formed in the plants and animals. For example, cellulose. Okay, cellulose is one of the components which is formed in the cell wall of plants. Starch, which we get from the potatoes, resins, natural rubbers, everyone knows about those. Okay, so this is the natural rubber, latex. Okay, silk, again, silk is nothing more than a polymer which is derived from the animals. Okay, well, semi-synthetic, as I said, semi-synthetic, these are the derivatives of natural polymer. Okay, for example, they take cellulose nitrate, cellulose acetate. Now, cellulose is a component which is formed in the cell wall of the plants. Correct. So they take it, they acetate it, and you get a cellulose acetate. You get cellulose nitrate after nitration of that. Correct. So therefore, these are the derivatives of natural polymers which are synthesized in lab. That is the man-made, or it can be formed in the industries. For example, what we have is the cellulose acetate, rayon, cellulose nitrate. Correct. So this is the experimentation by which they are showing you that is a rayon here. Okay. So this is the picture of cellulose and nitrate. Synthetic polymers. Now, synthetic polymers are 100% synthesized, manufactured in the labs. Okay, so these are the particular polymers which are synthesized in lab. For example, PVC, polyvinyl chloride. Synthetic rubber, they take this particular, they synthesize this entire rubber in the lab. Teflon, Olon, nylon 6,6. All of these are the various examples for synthetic polymers. Okay, so this is Teflon over here. Okay, nylon and Teflons. Well, when we observe classification on the basis of structure, as I said, on the basis of structure, we have the three categories. The first category was the linear polymers. Okay, so the linear polymers are, now we need to discuss about these. These linear polymers are nothing more than a chain-like structures. The characteristic is in these chain-like structures, okay, in these particular chain-like structure, there is no branching, right? Now, due to the chain-like structure, these particular things are closely packed. As these are closely packed, what is going to happen? These are going to result in having a very higher densities. Remember this, these are going to have a very high density. These are going to have a greater tensile strength. Okay, Due to this, it will have an effect on its melting point and the boiling point. So therefore, the melting point and the boiling point also are going to be affected. That is, it is going to have a greater melting point and a greater boiling point. Okay, so for example, we have HDPE. Okay, now HDPE is nothing more than a high density polyethylene. Remember this. Okay, so nylon and polyesters are nothing more than the linear polymer. So what we understand from a linear polymer over here is that when we take a look at the linear polymers, the monomers, what we have, they do not have any branches. Okay, so here a simple thing is the monomers are simply connected to the next monomeric unit by the help of a covalent bond, and that is nothing more than that. Okay, there is no branching between these particular chains. Okay, there is no branch, nothing. So as a result of which, these particular polymers are going to be held close to each other, resulting in higher density, higher tensile strength, and of course, higher melting point and bond. Okay, so this was about the linear polymers. Now, when we take a look into the next one, so this is a representation for the chain polymers or the linear polymers. Okay, so now branched polymers. So branched chain polymers are nothing more than, again here, what you're going to have is, if there is a particular, let's say there is a chain like this. Okay, so these are my linear polymers, right? Now, only difference between the branch chain polymer and the linear chain polymer is that in these cases, you will see that there is a small branching over here like this, somewhat like this. Okay, so due to the presence of smaller branches, what we call them as is the branched chain polymers. Okay, so the branch chain polymers are nothing more than a linear type of polymers, but with small amount of branches. Okay, so here the monomer unit are linked to each other by the help of the long chain, of course, by the help of a covalent bonds. Okay, as a result of the branching, these polymers are not closely packed. Now, there is a distance between one chain of polymer and the another chain of the polymer. Okay, due to this particular space, the density lowers down. Okay, so it has a direct effect upon its density, lower density. Due to the lower density, again, the tensile strength decreases, lower tensile strength because of the gap between them, and therefore they have the lower melting point and the boiling point. Okay, so the example for such one is the LDPE. Okay, the previous case we had an HDPE, that was a high density polyethylene, and here we have the lower density polyethylene. Okay, and what we see is the other example such as the starch and the glycogen. Okay, so let's observe the representation for this. So these are the branch chain polymers. Okay, so this is how it looks, right? Now, cross-linked polymers. Now, cross-linked polymer here, what is going to happen is the monomers which are forming these polymers, right? These monomers, let me represent over here. Okay, these are like chain-like structures again, the polymers. Okay, so what is happening here is when you take a look into these monomeric units. Okay, the important fact about the monomeric unit that you have to know here is that these monomeric units are bifunctional or trifunctional. Remember this. These monomeric units are going to be either bi or trifunctional. That means it is going to have two or three linking sites. So due to this, what is going to happen is that these monomers do not only form a covalent bond with the next unit, they also form the chain branches over here. Okay, they form the linking between the two monomers of two different chains here. Okay, due to which you will see that there is a link between the two chains, something like this. This is happening when your monomers are bifunctional or when they are trifunctional. Okay, so what we have here, these cross-linked polymers or network polymers. In such molecules, the monomer units are linked together to form a three-dimensional type of networks. These are expected to be quite hard, rigid, and brittle. Okay, example of the cross-linked polymers are like bakelite, galactol, or melamine formaldehyde polymers. Okay, kindly take down the names. These names are important. At least try to remember the bakelite or galactol. Okay, so as we have now, as we speak about the polymers, the classification of polymers on the basis of mode of polymerization. As I said, there are two different types of polymerization techniques. One is the addition, that is a simple one monomer adds up to the another monomer. Remember this. So there is simple one monomer unit which adds up to the another monomeric unit by the help of a covalent bond. So this particular monomeric units simply go on forming the chain-like of structures. Okay, so for example, we had polyethylene. Okay, so here what is going to happen is the polymers are formed from polymerization of monomer units which are containing either double bond or triple bond, right? So these are called as nothing more than your additional polymers. Now try to understand this. Now in case if both the monomeric units, if all these monomeric units which are involved in the formation of polymers are same, if they are same, okay, condition is if they are same, okay, that is all the monomers which are involved in formation of a polymers are same, then such kind of polymers we call them as, these particular polymers we call them as homopolymer. Okay, so when do we call them as a homopolymer? When all the monomeric units involved in the formation of a polymer are same. Okay, for example, yes, polyethylene. So here we have n number of ethene monomers which undergo the polymerization. When they undergo the polymerization, they are going to form the polymer which is called as the polyethylene. Correct. Now here all the monomers are same. Hence this falls under the homopolymers. In case if we are going to polymerize, but in this particular case of polymerization, we have, let's say, one over here is one type and here is the another type of the monomer. And when you try to combine two different types of these particular monomeric units, that particular process becomes a copolymerization. Okay, so we'll take a look into the copolymerization, and that is this Buna S, butadiene styrene polymer. Okay, so when you have this, that is a polymerization of two different monomeric units. A polymer which is formed by the polymerization of two different types of monomers, we call them as copolymer. For example, what we have is a Buna S. Okay, so Buna, butadiene styrene polymer. Okay, so what is happening here? You have a butadiene. Observe here, there is a butadiene, right? So n number of butadiene when they react with n number of styrene molecule. Now, when it starts reacting, what is going to happen is this carbon attaches to the previous molecule of styrene. Where it is attaching to the styrene. Where it attaches at this particular point. Okay. Now, this carbon, this particular end, what will happen first? This double bond gets shifted. Okay, so you can observe it at this point. This is where it has shifted. Okay, and this bond goes further. That is, it is used by this carbon atom in order to form the bond with the next molecule at this particular position. So what will happen again? This bond is shifted further. So there is a shifting of bond. So when you observe the entire polymer, you will see that the double bond is present over here. Okay, so this is your buna S, that is nothing more than butadiene styrene polymer. Okay, so this is about the copolymerization. Okay, so this was falling under the addition polymerization. Okay, so when we take a look into the condensation, now try to understand in addition polymerization, you do not have any byproduct. Byproduct in a sense, it is not giving you any amount of water molecule, neither any acids, nothing it is giving. It is simply adding the things finished. Correct. While if you see in these particular cases, that is whether it is a homopolymerization or copolymerization, doesn't matter. Okay, but when you see about the condensation polymerization, okay, so when we observe the condensation polymerization, the trick is here. The main difference between these both is that there is an elimination of water molecules. Okay, so the polymers which are formed by combining the monomers along with the elimination, right? Elimination of a smaller molecule such as whether it is water, alcohol or HCl. Okay, so this is known as the condensation polymerizations or condensation polymers. For example, 916,6. Now try to understand it over here. Now here, what is happening is this COOH, right? This OH and this H from this particular point. Okay, now here, these two things combine. When they combine, they give out water molecule. Okay, due to the result, this carbon, actually this is something like this, C double bond O, OH. Now, as I have taken already OH and I have combined with this hydrogen, this H2 has been eliminated. So, minus H2O, correct. So, as a result of which, what is going to happen here is this bond, that is this particular bond is going to be formed, that is C double bond O, right? This carbon is going to form the bond with this nitrogen here. As a result of which you will see it happening like this. Okay, so this is how it all happens. Here, a condensation polymerization usually eliminates smaller molecules such as water or sometimes HCl, etc. Okay, so this falls under the condensation polymerizations. Okay, so let's go further. Now, on the basis of the molecular forces which are present in the polymers. So when you observe the polymers, we usually classify it under the three categories again. So one is called as the elastomers. In elastomers, what is happening is that there is these particular polymeric chains are held together by the weak intermolecular forces. Okay, so they are been held by weak intermolecular forces. Right now, for example, we have the natural rubber, we have the bunion, etc., where the binding, there is the binding which is weak. Okay, and these particular weak binding forces usually permit these polymers to be stretched. As a result, it develops a stretching mechanism. And if you introduce a few cross links like these, that is between the two monomers, if you introduce a particular cross link between the two polymeric chains, that time whatever the polymer that you have stretched, it can be retracted to its original position. So what is going to happen? Whatever the polymer that we have stretched, if we introduced a few cross links in between, it can be retracted to its original positions. And this can happen only if we introduce a few type of cross linkings. Okay, so elastomers are nothing more than simple polymers in which these are held by the weak intermolecular forces. So first character, that is, these elastomers have the weak intermolecular forces. Correct. The binding force will permit these particular polymers to be stretched. And if you introduce a few cross links in between these chains, these polymers will retract itself to the original position. Correct. So after the force is released, again it is going to come back to its original position, as we have seen in the vulcanized rubber. Okay, what is vulcanization of rubber? We will see it in the future aspects of the classes. Now, fibers. The fibers are nothing more like a thread, like of the things. It is nothing more than a thread, which can be woven into fabrics. Okay, so for example, rayons. Okay, so these are widely used for making the clothes, nets, robes, gorgets, etc. Okay, now these particular fibers usually contain a high tensile strength. Okay, because these chain possesses a very strong molecular forces such as the hydrogen bond. Okay, now what is exactly the hydrogen bond? Hydrogen bond is nothing more than when you have the polymers, okay, there are the strongest forces of attractive bonds which are produced between the chains. Okay, now it is usually produced when the oxygen is there, nitrogen or any other electronegative element is connected to hydrogen. Okay, and the same electronegative element or some other electronegative element is there exactly at the bottom chain. So that time what will happen, it gets attracted to the next electronegative element. So due to this, the hydrogen bond is created. Now, when the hydrogen bond is created, what is going to happen? This will have a higher tensile strength. That means it will become compact. Density increases. So therefore, here the tensile strength increases because the chain possesses a strong intermolecular forces such as the hydrogen bonding. The fiber are crystalline in nature. Okay, these particular fibers are crystalline in nature. They have a very sharp melting point. That means at the perfect temperature, it starts to melt. A few examples of this particular class are like a nylon 6,6, terylene, and polyacrylonitrile. Okay, so these are all about it. So let's go with the next one. Thermoplastics and thermosettings. Okay, the thermoplastics. Thermoplastics, actually, these are the linear polymers, actually. Okay, these are linear polymers and have very weak van der Waals forces in them. Okay, now due to this, what will happen is, because of the van der Waals forces which is acting in other chains, these forces are intermediate forces between as present in the elastomers. That means when you compare the strength of the van der Waals forces acting in the chain and the force which is present in the elastomers, okay, and the fibers. That means if there is an elastomers, I'm going to take over here elastomers. Okay, and if I'm going to take over here a fiber, the fibers are nothing more like a rope-like thing which you can weave it into the fabrics, correct? So if I'm going to take here the fabrics, okay, so if we take over here the fabrics, now this thermoplastics are going to stand in between these two, okay, because of the presence of the weak van der Waals forces which are acting in various chains. These forces are of the forces intermediate than that of the elastomers and in the fibers. Now, when you heat this particular thermoplastics, what will happen? They are going to melt and they are going to form a fluid. And if you pass those particular fluid into a mold, okay, it will take the shape of whatever mold that you have passed it into. That is, you can set it into different shapes. And on cooling, it is going to become again a hard mass. Thus, these can be casted into different shapes by using suitable molds. Okay, for example, polyethylene and polystyrene. So all these particular materials which can be heated okay, which you can heat them, convert it into a liquid, and again remold them. You can recycle them. Okay, such a particular plastics, we call them as the thermoplastics, right? The another thing is that the different type, that is thermosetting. Now, thermosetting plastics are those particular plastics, if you just heat it once, if you just set it once, you cannot change the structure, you cannot reuse them again. Okay, so these are the polymers. These are the polymers which undergo a permanent chain on heating. This, if you take this particular things and if you heat it, okay, what will happen is it will generate more amount of cross-linking once you heat it again. Okay, so they undergo extensive cross-linking once you are going to heat it. Okay, due to extensive hard cross-linking, they are going to become hard and infusible. They cannot be recycled. Okay, for example, bakelite, melamine formaldehyde, urea formaldehyde resins, etc. Okay, so you can just heat it once, you cannot recycle. Okay, so that is the basic difference as what you can see between a thermoplastic and a thermosetting. Okay, so what are the difference between a thermoplastic and thermosetting? Usual asked question. So upon heating, okay, they soften and readily can they take the shape. Okay, they can regain the shape even after molding. Okay, so you can give it a shape, and once it is cooled, it becomes hard and it is going to take that particular shape of the mold. Upon heating, they do not soften. They only melt and they cannot be remolded with in the case of the thermosetting plastics. So these are the first differences between the thermoplastic and thermosetting. In second case, if you see in the case of the thermoplastics, these are generally the long chain polymers and formed as a result of addition polymerization. Okay, so in this case, generally these are cross-linked, okay, in nature, and these are formed by condensation polymerization. So in condensation polymerization, I already told you that whatever the monomers which are involved in the formation of polymers, these monomers are usually bifunctional or they are trifunctional, correct? So once you heat it again, it is going to form more number of cross-linking by the help of these more bifunctional groups or trifunctional groups present in the monomers, right? So now when you take a look into the third aspects, the thermoplastics are generally weak, soft and less brittle, while thermosetting plastics are comparatively hard, strong, and brittle in nature. Okay, so these are the differences between the thermoplastic and the thermosettings. Okay, so the type of polymerization on the basis of the chain group polymerization or addition polymerization. Now here we are going to speak about the entire reaction conditions. Okay, so we are going to speak about with respect to how these particular polymers are going to react, which type of mechanism it is going to take up, and how these particular product polymers are formed, which we will do it in the next slide. Take care. Thank you.